Now we have come at the second part, how to build one yourself, which, as I told you, I was inspired by this kid, Tiago Olsen is his name, from Michigan, who did it. He really did it in his parents' basement, I think, or in their garage or something like that. Started when he was 15, took 2 years, bought everything himself. It cost him like $3,000. And I was at that time, when I read that, I was with some friends in a group experiment, and we were doing something on chaos theory, and it was extremely boring. It wasn't going anywhere, so when I read this, I thought, we can do this. And I suggested it. Well, they were kind of skeptical, but we did it eventually, and the next slide. And here's what you need. Well, obviously you need a location, and that was actually the hardest part. We found an abandoned classroom in the main physics building in Utrecht, and as soon as the word got out that we were going to build a nuclear reactor, all sorts of people tried to, stop us from doing that. So, for some reason. And one thing they tried was they made us file for a license, and we did. We filed for a license to ask if we could build a nuclear reactor, and we didn't get the license. We tried again. We thought, we can wing this thing, so we tried again, and instead of asking if we could build a nuclear reactor, we asked if we could research what happens when you get a 20 milliamp plasma discharge at 30 kilovolts in a particle fusion. And we got it. And we yielded some very surprising results. Well, next thing you need is a vacuum vessel, as I showed before. It should be large enough to fit, in our case, a 6-inch outer sphere, the one that's grounded. Then you need a small grid. You need the big grid itself, gas, and 2 mechanical pumps, because they both work on a different range of atmospheric pressure, and we need to go deep down. Then detection and measurement equipment, of course, because you need to detect the neutrons that you produce to be sure that you've actually done it. But also you need to be able to measure the pressure. And for radiation safety, very important, of course, some lead sheets to shield yourself, paraffin bricks against the neutrons, and a Geiger-Müller counter to see, you always have to carry one, and if it starts clicking, you have to get out of there. This is what they always say, nobody ever does. But, once you're in an accident, you will. Then there's the high voltage throughput, which is a very important part, and typically the hardest part, because you need to transport 30 kilovolts from atmospheric pressure through the wall of a chamber into a vacuum. And, well, the good thing is, I told you the other kid spent $3,000 on it. We found a basement in the university, in the building where they had the old particle accelerator, where they had everything except this. So we found everything. We went with like shopping carts, like at the end of the day when most people left, and we went into the basement and just loaded up and then went back so nobody would notice. Except for the grids, because they were of course, they had to be made, and we're not that good with it, so we had them made, but we didn't have to pay for it because it wasn't in the university, it was in the workshop. And the gas inlet was somebody bought, but I don't even know how much it was, like 50 bucks. Well, what you also need, apart from the things in the shopping list, is some friends to do it with. I mean, I would have never done it without them, or with the 2 people listed in the bottom. One was the supervisor of the experiment we were actually doing, and the other one was an old man. He just retired from the particle accelerator, and I think he liked the smell of radiation. He loved this experiment. So here you see us working on all the different parts we assembled, and eventually we got to this. This is the thing. It looks like a rocket. It is not. You see the 2 mechanical pumps here, the vacuum vessel's there with a window so we can actually see what it did, which is good because it's really pretty, as you can see. The high voltage throughput on the top, and then all the measuring equipment in the rack on the right side. And here in the later stadium, we added the lead sheets because it turned out to be a little bit more radiation than we thought. The neutron detector is the white thing right behind that. And the high voltage throughput is now attached to the power source. And you see a bottle of gas, which wasn't on the list, but obviously you need the actual gas itself. Okay. So this is the grid. This is the thing that's going to do it eventually. This is we had this made because it was. I cannot do this. We designed it ourselves though, but we had it constructed. You see the inner grid. It's made of tungsten. It's very small, so it's very transparent. The outer grid has far less strict demands, so it was made of some other material, a cheaper one probably. And then this is all ceramics, because it has to be non-conductive, isolating from the whole thing, otherwise the whole thing would be on 30 kilovolts. This is the top again, with some other contacts, it's not that important. And this is from the inside, with a filament. You can see this is like a light bulb. This is the filament, we actually use it to ionize, to create plasma. It's like a little help. It emits electrons and they knock out electrons that are in the other gas. So it's not that important, but it makes a nice picture. Next one. Here you see how everything's connected from the inside. Okay. And so now it was built, which meant that it was leak-free. So we got to do the test. The first test we did was in a vacuum, trying to get it up to 30 kilovolts. And this is a lot harder than you think it is, because 30 kilovolts, it's a very high potential. It's basically like lightning. We had a lot of lightning, or discharges from one part of the metal to another part that was non-conducting, or even to the outer part. Because, so we had to do minor adjustments a lot until we could get it up to 30 kilovolts and it would stay there. Then the second thing is, you'll try to make your first plasma. And we do that with argon, because argon is inert, and if something goes wrong, the argon at least won't do anything. But so once that worked, you want to try something else, because argon is very different from deuterium, because it has 18 electrons, 18 protons, so it ionizes differently. There's a whole bunch of stuff why you want to eventually try it with hydrogen. But hydrogen is highly explosive, so you don't start with that. You want to make sure everything is fine until you start with hydrogen. But it behaves exactly the same as deuterium. So once we did that, yeah, here you see on the vacuum. So there's nothing happening here, we thought. But, so it was on the high vacuum, the pressure was about 1 billion times as low as it is here in this room. And we got it up to 30 kilovolts, and all these weird colors started showing up. And we were all like so amazed by this, and it's kind of pretty. So we took some pictures and posted on some forum saying, you know, what is this? And they said, yeah, you shouldn't look at that. Which is probably why 15-year-old kids or 19-year-old kids should not be allowed to make reactors. We didn't after that. Well, there's a close-up. Yeah, next one. Here. You can see that the ceramics turned pink for some weird reason. We still didn't figure out why though. But there was a lot of X-rays coming out of that thing. So all the germs on my forehead were killed. And I hope it stays at that. And then we started to do the first runs with the filament on, so you cannot see it very well, but you can see that there's a light, like purplish spot within the sphere. And this is on the very low, intensity. We amped it up a little in the next one. And yeah, so here you can see why this design is basically flawed. This is still very low intensity, but the sphere itself, the inner sphere, is starting to glow already, like an ordinary light bulb, because it's going to reach its melting point soon. And this is not even very high, but so it is. Well, yeah, just give me the next slide. Yeah. Now this is a little bit higher already. We turned the filament off, and it gives nicer pictures. We found out that the filament, it was hard to put it in there, but it doesn't actually do anything. Without the light, you see the plasma pattern. This is argon. It has a very typical color compared to hydrogen, which you will see in a minute. Yes. See, this is on the higher condition. So the more gas we let in, the more particles hit that inner sphere, the hotter it gets, and eventually it will melt. So that's why it's limited again. Now this is hydrogen. You can see this is a slightly lighter color. You don't want to see, the weird thing is it looks so pretty, but you're not allowed to look at it because it's so bad, which is kind of sad. Next one. This is from the outside, so you can see the vessel itself. We dimmed the room. So this is it's almost like an ordinary neon bulb. That's basically the same thing, except it's a very weird construction, and it can also fuse stuff, which we did after this. I think this is the last picture. Yeah. So it worked. We had positive hydrogen test runs, so we were ready to do the deuterium thing. So we had to add some extra safety measures, so remote control operation. and paraffin, the paraffin-brick walls, which slow down the neutrons. As you can see here, this is where we operated from. That's all paraffin with a little mirror so we could see what it was actually doing without having to look in it ourselves. And the next one. So this is the reactor itself from the top view with the neutron detector right there. See, the paraffin slows down neutrons, but it doesn't capture them because neutrons are not easily captured because they're neutral. They don't interact. You can't slow them through collision, and once they're slower, they're less dangerous. Which is basically, it's the best we got. This was actually pretty good. People were impressed by this. Because who has this amount of paraffin? Universities do, apparently. Okay. So, what are the results of this thing? The pictures you just saw. The highest neutron production rate was 150,000 neutrons per second, which is, because of the 50-50 rate, is about 300,000 fusions a second. That adds up to 1.4 times 10 to the minus 7 watts, which is not that, it's very little output power. So even if you calculate the Q factor, you see that we needed about 10 to the power 10 times as much input power as we got out, which is horrible. And to put that in perspective, it takes 67,000 joules to boil enough water for a cup of tea. With this machine, it would take 15,000 years to boil a cup of tea, to boil enough water for a cup of tea. So that, and thankfully, because if it would have been more, we would have not wanted to be in that room. I mean, it was safe for us to be in the same room because there was so little energy produced. If it would have been more, we would have to take more distance and build big brick walls and doors that lock, stuff like that. Okay, next slide. So to conclude, you don't expect any fusion power plants in operation. I'm sorry, Brian, but not in the next 50 years, right? It's going to take a long time. They're going to build this EVA thing, then they're going to build another one, and they both need 20 years of testing, so it's going to take a very long time. And don't believe anyone, if you ever meet one, who says there's free energy, or there's like this fusion thing this big that can produce energy, but the government is trying to keep it away from us because they're evil. That's not how it works. And if you want to build your own, or are just interested, visit this website, www.fuser.net. It's basically, it's where everything is coordinated from. They have a very active forum, so if you ever have questions, they told us about the radiation from the high vacuum, the purple stuff. And they also keep a list of who's ever done it, the neutron list, so cool. And there's like 50 people, 40 people on it right now, including me and my friends, but it could be a lot longer, so it would be cool if you would try. That's it.